Hello, 705. I'm a big fan of Chapter 7. I like how it merges two of the previous chapters that we've done. We talked about demand back in Chapter 2, I believe, and we talked about these demand functions, and you had quantity demanded depending on price, income, prices of related goods, and then we also later on jumped into the idea of regression, estimations, ordinary least squares, coming up with using data that you've obtained and kind of applying a theoretical model to it and seeing whether the theory holds with the results from the data that you've been using, that you've been analyzing. So I like Chapter 7 because it kind of, again, merges both of those ideas, and we have a theory about how demand functions work, and we can take actual real-world data and find out whether the variables we think are theoretically important to the demand for our product actually hold up in reality. So there's going to be different ways that you can try to estimate demand for a particular product, and of course marketers, advertisers try to do this in lots of different ways. A pretty basic way is just going out and asking people how much they're willing to pay for things or what they might think about different price changes, sale on something or a price increase on another thing. And it's probably an easy way to do that, and you might think it's a very direct way, a very accurate way, I suppose. Just go up and ask somebody what they think, because you're talking to the people who are potentially going to buy your product. Of course, there are problems with that, otherwise it wouldn't be at the very beginning of the chapter. So there are problems with this sort of consumer interview technique. For one thing, I guess you have to think about the fact that unless you're stopping every single person who walk into the store, and you'd have to include also the people who aren't buying your product, which might be kind of hard to do. If you just sat there at the end of the cash register, you'd miss all the people who weren't buying anything at all, or you'd be missing people who maybe looked at a particular product and then maybe saw its price or some other aspect and then decided not to buy it. So if all you did was look at what people actually bought, you'd be missing what they didn't buy. So interviewing consumers like that, I guess at the end of the grocery line, you're not getting a complete picture of what's happening. And again, it's very unlikely that you're going to be able to interview every single consumer that's out there. So the people that you do interview might not be representative of the entire population of consumers that you're interested in. There may be what we call response bias, where the person responding to your question may give you an answer that maybe they think you want to hear, or they may give an answer that makes them, the consumer, puts them in a better light, maybe. There just may be lots of other reasons why what the person says they will do is not actually what they are going to do or what they end up doing. They might actually have a belief in their minds that they're going to pursue a certain action, and then when it comes down to it, they do something different. And the consumer might not have known actually at the time they had the interview that they were going to make a different decision. But again, it's just these issues aren't very easily uncovered in the process of an interview like this. It might just the respondent might not know exactly what the answer to the question is. They might be confused about the question if it's written on paper, especially. There might be errors of interpreting what the question is asking. So the respondent might not actually know what the question is asking. They might not be able to answer in an accurate way, or at least in a way that the interviewer is hoping they will. Kind of a step up, I guess, from just the interview method that sort of increases the quantitative rigor, I suppose, are market studies, experiments, where you are allowing your consumers to behave in a way that they, quote, normally would. You're not just asking them what they're going to do, you actually observe them making the purchases or not making the purchases. But of course you're still observing what they're doing. So in a, again, market study technique like this, then you're controlling some things, but you're trying to give the consumer a little bit more flexibility, and trying to introduce a bit of reality into the situation. So you're actually allowing them to purchase the product or not. These can, again, introduce a certain level of reality, but still it's usually somewhat removed because it's a controlled experiment, and for one thing, you're trying to get volunteers to do this. You're not actually canvassing every single consumer that goes into the store. You're trying to hold everything else constant except a particular price of something. And so, again, there's more reality to it, and then maybe not as much reality as you would hope. You can actually try to go out and observe what consumers are doing with these field experiments, and maybe running a particular product in one store with a certain price, and then that same product at a different store across town or in a different town, charging a different price. So again, there are different ways you can add levels of reality into situations like this to try to obtain better results or more consistent results. course, a way that economists tend to prefer are these empirical demand functions, where we talked about demand functions back in Chapter 2, and how, again, quantity demanded depends on the price of the product, prices of related goods, income, that sort of thing. And so, if we can obtain data on what people actually purchased, or at least their demand for a certain product, and you could also fairly easily obtain data on the prices of that particular product. You can maybe get proxies for income. You can get prices of related goods fairly easily. That's the kind of stuff that economists tend to like, because again, you're not asking someone how much they're going to buy. You're not putting them in this kind of fake experiment where they're in a room and they're pretending how much they want to buy, but they're not actually using their own real money or anything like that. And they're not going to go home at the end of the day with the product that they're pretending to buy. But you're actually using data from actual purchases and actual consumers without really sort of interrupting them and saying, hey, I'm going to observe you and see how much you want to buy. So you're not really interfering too much, but you're just seeing how much they buy, and then you're collecting data on these other variables too, and seeing, again, whether the theory that you've developed it holds true. And again, since you are observing people in kind of the most natural setting you can, then it tends to be true that it's the most useful in being able to make future predictions based on the results that you've gotten. Because the results you got were hopefully, again, obtained in a fairly natural setting for the consumers, then extrapolating from those results should be fairly consistent and fairly reliable. Because again, in the future, it's as natural a setting as it was in the past with the data that you've collected, because you haven't interfered with the consumers at all. So as we mentioned, a basic demand function that we've seen many times in the past just has this sort of linear form where quantity demanded depends on the price, income, prices of related goods, substitutes, and complements. And again, like I said, we've kind of seen this before. Going out and actually estimating it, again, you get this linear form, and you can interpret the coefficients as basically the slopes, or the partial derivatives, if you want to think of it. So the B coefficient there is how the quantity demand changes when the price changes. The C coefficient is how the quantity demanded changes when income changes by 1 unit. The D coefficient is how the quantity demanded for one product changes when there's a change in the price of a related product. We have some expectations of the signs of these coefficients, maybe not so much the magnitudes of the coefficients, but at least the signs of them. We expect that, because of the law of demand, we expect the B coefficient to be negative, the law of demand to be true. As the price goes down, people would buy more of it. We expect the C coefficient to be positive for normal goods. As income goes up, people should buy more of the product, or demand more of the product. If it's an inferior good, and again, we define inferior good just basically as this description here, when people's incomes go up, if they were to demand less of it, then we say, okay, that's an inferior good. The D coefficient there should be positive for substitutes. If the price of Coke goes up, we expect the quantity demanded of Pepsi to also go up, because of it's a substitute for Coke. If they are complementary goods, then we expect that D coefficient to be negative. If the price of peanut butter goes up, we expect the demand for jelly to go down. Once you have your estimated coefficients, you can come up with the elasticities fairly easily. And this will, again, go back to the elasticity chapter, where we had I believe we wrote it out as the elasticity was either the dq over dp times this ratio of the actual price quantity combination you're interested in. So it was like dq dp times the price over quantity that you're interested in. Here we can kind of restate it, because the beta hat there, the estimated B coefficient is basically the change in Q as a result of the change in the price. So we can say the estimated elasticity at this particular the price quantity combination is this estimated B coefficient from the regression results times whatever that P and Q combination that you're interested in. The income elasticity is that estimated C coefficient times M over Q. The cross-price elasticity is that estimated D coefficient times the related product price over the Q. So how do you actually go out and estimate these demand equations? Well, it's fairly straightforward, and it's going to just follow a lot of the same steps that we specified in the regression chapter. So you just figure out what you think the theoretical basis for demand is. You want to specify this firm's demand function. So again, coming up with what you think, if you think the income is important, especially coming up with what you think the prices of related goods are going to be. What related goods do you think are important? What products do you think are substitutes for yours? What products do you think are complementary to yours? So that's kind of step one. Of course, including the price of your own product and including income should be important. And again, most of the major decisions is just going to be how you're actually going to come up with those related goods. What goods are going to be related for you, for your product. Step two, again, is probably the one that's the most time consuming, but actually collecting the data for the variables that you think are important. The income data is probably going to be tough to get. Your own price and your own quantity demanded shouldn't be too bad. The prices of related goods may especially be tough if it's proprietary data. It might be hard to actually get the price of a particular product as it changes over time. You can get broad categories, like if you go to the Bureau of Labor Statistics and look in the Consumer Price Index, you can get individual prices for individual types of goods, like jeans and butter and milk and bread, things like that. Healthcare, apartment rents, that kind of thing. But again, it's going to be fairly general. It's not going to be company specific. Step three is the fastest. Once you know what the data is, once you know what your theory is, then you just run ordinary least squares, and that takes, again, like a tenth of a second in Excel. So it's fairly fast. It just kind of happens after all these really slow steps that precede it. But again, it follows a lot of the same procedures that we outlined in the estimation chapter, in the OLS chapter. Okay, one way that you can estimate demand is to think about how it changes over time. When we talked about the pizza demand, I think back in chapter, well, I guess it was in the estimation, no, it was in the supply demand chapter. We talked about the demand for pizza, and we had, the price of a slice of pizza, the income, well, actually it was the college tuition in a college, well, the tuition in a college town as a proxy for income. We had some of the prices of a can of soda, I think, as a complementary good. And what I remember talking about it is, let's say you have a lot of different college towns, and you got all this data, basically every row of your Excel table that you're going to run a regression with, every row was a different city. Every column was the different variables that you were using. And that's one way you can do it, where your sample is a bunch of different cities, and you're estimating demand amongst all these different cities. And the coefficients that result would sort of be an average or a kind of generalizable coefficient among all of the cities that you're talking about. Another way you could do it, though, is to say, well, let me just stick with one city, and I'm going to stick with one city, but the different rows of my table are going to be the different years. So instead of looking at pizza demand in the year 2012 in Shreveport and Ruston and Monroe, why don't I just stay with Shreveport and say, well, let me collect all that data, but instead of doing it for different towns in 1 year, I'm going to do it in one town for many years. So I'm going to get the quantity demanded, the price, the income, prices of related goods in Shreveport for the year 2000 and 2001 and 2002. And again, a benefit of doing that is you're holding a lot of other things constant. There may be situations that you can't really quantify very easily, differences in Shreveport and Ruston that aren't very easy to quantify, which if you decide that you're only going to stay with Shreveport, you don't have to worry about collecting those variables, because presumably that sort of Shreveport-specific variable is going to sort of stay the same if you're doing this time series version of it. So a simple way of figuring out how demand changes over time is just to say, well, let me just set up an equation where the quantity demanded just depends on time. And so you have this QT, the quantity demanded, depends on some intercept term. And the only other variable that we might think is important is this time variable t. And I had to make this change. I don't know if the book has this little equation off to the side somewhere or in the text where it looked like B and then there was a t subscript, just like there's a t subscript on the Q. But technically that's not right. It should be A, this intercept term, plus B, this time coefficient, times a variable t. So if that's not the way that it is in your book, you can scratch it out and call the textbook publisher and complain about it. But it should be, again, the demand depends on A, this intercept term, plus this B coefficient times the t, the time variable. So if we think about what's going to come out of this, you get regression results. And again, you're going to get, there shouldn't be a hat over the Q there, lots of changes. So the relationship that's going to result is you get this estimated coefficient for A, the intercept term, plus you get this estimated coefficient for B, And then once you have those, you can make some guesses, you can make some predictions about, well, if I plug in a particular time variable, or a value for the time t, then I should, using the estimated a and b coefficients, I should be able to come up with a prediction for this q variable, the demand variable. So again, it's a fairly simple form, but it's useful in a lot of cases. You might think that sales for your particular product increase over time, and so you might hypothesize that the b variable is positive. And if you get, again, a b coefficient that is positive and significant, you say, okay, it seems to be the case. So maybe, I don't know, car sales or computer sales or something like that. Sales that just tend to increase over time. If you get, again, this positive coefficient that's statistically significant, you say, okay, that seems to be true. Sales do increase over time. If your b coefficient is negative, or you expect it to be negative, then that indicates that your sales are decreasing over time. If it shows up close to zero, or if it shows up insignificant, then you might say, well, sales seem to be relatively constant. And again, you can test the reliability of these estimates by looking at the coefficient itself and then the p-value to see whether it's significant or not. So again, it's fairly basic. You're not including any other variables in there. You certainly could. You could include the price of the product. You could include the income and the prices of related goods. Hopefully those things would change over time too. The t variable would change, obviously, but hopefully those other variables would change too. It would be a little weird to, maybe if you had daily data on these things, if the price of your own product stayed exactly the same over an entire year, and let's say you got 365 days worth of rows of data, and if the price variable stayed exactly the same, then your your results are going to be kind of weird because your p variable is not fluctuating at all. But you certainly could add other variables to this kind of simple linear form. But again, this might be a first pass way that you go about it. See if the time seems to matter. So you get some basic data that might look like this, and you can just sort of see visually that there's this upward trend to it. And again, coming up with forecasts from that, you can sort of eyeball things, and if you have the data in Excel, then you can plop a trend line in there, a linear trend line. I think we talked about how to do that. You can also, there are ways that you can tell the trend line function to come up with future forecast, to make this estimated trend line, to make the line extend further out beyond the data that you have. And again, you can kind of eyeball it that way and say, well, this is what I think the sales are going to be. One thing you might notice is that the dots that are on the screen there don't ever really hit that red line. Some of them get kind of close, but they don't ever really hit it. And so again, you might want to include that if you're using this estimated trend line to come up with predictions for the future. You certainly might want to suggest that, well, this line itself hasn't really gone through any of the points, so there's a sort of a degree of error into this. But you can explain to your audience what r squared means and all that stuff. Okay, so we have Terminator, Pest Control, and we have the monthly data there, and you can see that, well, one way that you might think about, well, how do I collect the data for this? Well, I know that in January 2007 I had this many sales, QT. So you might start out with just with two columns, a month column and a QT column. And you might have, your month column might have dates that have been written in exactly as they are in this table. So January 2007, February 2007. Of course, when Excel tries to run a regression, it doesn't know what to do with words. And so it sees January and it says, well, I don't know what to do with that. So you have to create this time variable t that you see there. And so we create this variable, and we have it increase by 1 every time there's a new month. So your t goes from 1 to 15 in this case. So again, you have to kind of transform your month variable into a variable that is quantifiable. And it's fairly easy to do in Excel. You just have this, you just make this new column t, and you start at 1, go to 2, and then you can just kind of copy and paste that thing all the way down to the bottom of your data, and it'll do it, again, really quickly. So you plot the individual QTs there as your vertical axis, and the t variable as your horizontal axis, and you get a picture that looks like this. Homes serviced per month. I don't know, I used to be a managing editor at a journal, and my eyes kind of noticed things like that. I don't know why they would include that gap between the SER and the Weist over on the vertical axis. Again, call a textbook publisher, get that person fired. But you draw your trend line through the data, and you can make some, you can extend that line in Excel. The other thing, though, is you can use the data that you have and just run a regression. And you can say, well, I want to have Q as my dependent variable, and I want to have T as my independent variable. You can either run a regression, or again, in the trend line feature in Excel, you can not only have it draw the linear trend line, but you can select the option to give you the equation of the line and the r-squared also, which is nice. The only bad thing is that you can't have it report the p-value for the t variable that's there. So even though I see that the trend line has a coefficient on t as 4.53, I don't know whether that's significant or not. If it's, I mean, I'm sure it is because it's of how steep this line is sloped, but it may not be. Also, another thing to say is you can see that trend line equation, QT with the hat over it, equals 46.57 plus 4.53. And it looks like that t is a subscript. It shouldn't be. It should be 4.53 times t, because it's getting multiplied by all of the t variables that are there. So again, scribble that out in your book, write it the correct way. The nice thing about having this equation then is that you can make predictions beyond that t equals 15 point, because the data only go through March 2008, but I might say, well, what happens in April 2008? And how do you make that prediction? I have this equation, and you can extend that line, but I want to figure out what number should I associate with April 2008? What number for QT should I associate with March 2008? And once you have that little equation, then you can just plug in the t that would be associated with April 2008. April 2008 would have a t of 16. And so I have this equation, 46.57 plus 4.53, and I can multiply that by 16, because that's the value of t that I'm interested in. And I get this estimate of 119 sales. And you can keep going, plugging in values of t for 17, 18 if you want to go to May and June 2008. And you get these different estimated values of QT for that. One thing that certainly crops up in a lot of different industries is seasonality, cyclical variation. So if you're thinking about construction, then they go gangbusters in the spring and summer and early fall, and things kind of slow down in the winter. Maybe not so much in the South, but since I'm a Yankee, it certainly is true up there. So there are these predictable swings in sales for construction. To the extent that we can, we want to try to account for everything that we know is important. And so we say, well, I know that price is important in demand, I know that income is important, and I know that prices of related goods and services are important. Well, seasonality might be important too, or maybe even something like a business cycle would be important. People tend to really want to buy my product when the economy is doing well. When the economy is not doing so well, we don't see as many sales. You might think of refrigerators as like this, because when, for a lot of people, there's probably very few people that actually buy a refrigerator because their old one completely dies and they just can't do anything else. A lot of people are kind of like, well, it's kind of old and we could go with getting a new one. Well, if the economy is in a recession, people probably hold off on that. And they say, well, really, ours doesn't work too well, but since things aren't very good right now, let's just wait. Whereas if it's in an expansion period, people might be a lot more open to getting a refrigerator, even if their old one's not working so well. So there may be, again, for certain industries, certain markets, the season may be a factor that matters. And for other products, or even the same products, where we are in the business cycle might matter also. If you don't account for those things, then again, you're sort of leaving out something that you know is important. And so, but there are easy ways that we can account for seasonal variation or cyclical variation too. One simple way you can do it is the dummy variable technique. And we talked about dummy variables, I believe, when we did the auto example, when we had the foreign variable was a dummy variable. We also had one in the pizza college town example, when we had whether the college was in an urban area or not. What the dummy variable does is it probably gets into a little more complexity than we need in this class, but it sort of shifts the intercept term, and so you sort of retain the slope coefficients that you had before. The B variable, the C variable, the D variable on your price, income, and price of related goods. But since there's this W variable, it kind of makes it jump up. And it'll kind of be clearer when we look at a picture in a few slides from now. But if you include a dummy variable for the season, if you're thinking of the construction market for new housing, then you might have a dummy variable for the summer. And every time that's, for every every time you're looking at data on house sales, you would include a 1 when the sales you're looking at are for summer sales, and a 0 for sales that are in the winter or late fall or something like that. If being in the summer is important, then you would see that the p-value for that summer dummy variable would be significant. If it's not important, it's insignificant, and you can kind of, well, you wouldn't want to toss it out, but you could say that, well, I tried accounting for seasonality and it didn't seem to show up as being significant. So again, if you just observed the data and you weren't sure whether there's seasonality there, you might get something that's pretty severe like this, and you go, well, yeah, obviously the fourth quarter seems to be pretty high, so this might be something for a retail sales product. Lots of high retail sales in the fourth quarter, Christmas. We tend to think of seasonality in this way, that yeah, fourth quarters always tend to be big. But again, it depends on the market. So for certain products, again, housing construction might be really strong. Not necessarily in the quarters either. It might be strong in June, July, and August, which June is kind of the ending of the second quarter. July and August are in the third quarter. So you might have seasons this way, like first quarter, second quarter, third quarter. You might want to do it like that. You might also have monthly dummy variables, or you might have a dummy variable that is just the summer for June, July, and August if you want to do that. Or May through September, whatever you want to do. You could have a variable that's May through September, and you have that as a 1, and then all the other months you just have as a 0. So there's lots of different ways you can play around with it. But again, if you have a situation like this and you go, obviously seasonality seems important, and so I should have a fourth quarter dummy variable to try to account for that. I may have mentioned in class, and I don't know if I did it on the other videos, but if you're going to include dummy variables, let's say you want to have a dummy variable for, or you think that there might be seasonality between the 4 seasons, spring, summer, fall, and winter. You actually don't need, even though there are 4 seasons, you don't need 4 dummy variables. The whole point of a dummy variable is you have it kind of a light switch. It's either a 0 or a 1. It's turned on or it's turned off. Well, if I had a spring, summer, fall, and winter dummy variable, then one of those is going to be a 1 all the time. The rest of them are all going to be 0s. And it's kind of irrelevant to have, let's say, a winter dummy variable in there. Because if the spring dummy variable is 0, and the summer dummy variable is 0, and the fall dummy variable is 0, then obviously what has to be happening is that sale is happening in the winter. So you only need, if there are n seasons that you want to account for, if there's n time periods that you want to account for, then you need only n minus 1 dummy variables in your equation. Because again, it's sort of the excluded case, the case where all your other dummy variables are 0, is going to include the one that you're interested in. So again, you might have had, well, I think that for construction, sales are going to be strong in May through September, and that October through April, our sales are not going to be strong. Well, you wouldn't need to have a dummy variable for summer and then another dummy variable for not summer, I guess. Because, well, if the summer variable is 0, then it's not summer. And so you wouldn't need that. You just need 1. Just need 1 dummy variable for that. Okay. This just kind of describes how you assign variables, what you type into Excel, but it's pretty straightforward. If it is summer, then you just put in a 1 when it's the summer. If it's not the summer, then you put it in a 0. It's pretty clear. Again, what happens is, and you might have noticed this before, if you looked at that little scatter plot that we had before, if you drew a line through the non-fourth quarter dots, it might have looked like what the bottom line does here. You kind of have this linear line that flows through it. And if you drew a line through the fourth quarter dots, then it tended to be of the same slope as the line that was below it. So what this seasonality does is it tends to it keeps the steepness of the line the same, but you have sort of this intercept shift. And that's what basically the dummy variable does, is it kind of creates a new intercept for those particular seasons that you're accounting for. Again, it might be a little more detail than you need to know, but that's what's happening. Okay. There are other ways that you can kind of estimate these things, and I'm kind of focusing a little more on Excel here. You can just sort of look at what's happening, look at your data, and plot different trend lines in Excel. So if the raw data is there in the upper right, you can throw a linear trend line in there. In the if the raw data is in the upper left, then you can throw a linear trend line in there with what it looks like in the upper right. You can do exponential trend lines. This might be something for if you're looking at maybe tablet computer sales, where they tended to be pretty low because they're fairly a new invention. early on, and they've just been kind of taking off the last few years. That the scatter plot data might be better fitted as an exponential trend line. In the raw data that I have here, it doesn't seem to be doing that. But you might think about data that kind of increases at an increasing rate, and if that's what your scatter plot looks like, then obviously a straight line might not be a very good job, might not do it very well. But an exponential might do it, or you might even have a quadratic equation might do a good job at that too. You just kind of maybe play around with the different types of trend lines to think about. Excel also, in the lower right hand picture there, Excel also will allow you to draw in forecasts. If you have it include the equation too, then you can do your own forecasts as well. But like I said, it'll give you an R squared, and that's helpful, but it won't give you the p-values, so you don't know if the trend coefficient is significant or not. So a little bit of caution with that. Okay. You might think about other ways that you can forecast particular trends. One thing you might kind of find to be an easy way to do it is just take the average of the sales that you had in the past. So we had particular numbers of sales, and I'm just going to say, well, I think a good way to forecast future sales is just take the average of what we've had in the past. And that's decent at certain times. It's not a good thing to do if there are noticeable trends, if there's noticeable up or down trends in your data. And it might be a little clearer if I kind of take a picture. So let's say you have data that tends to be trending upward like this. Well, what you would expect, just by looking at the dots there, is some estimate or some future prediction that is kind of like where the green dot is. The green dot seems to be following the trend that's happening here. But if you take an average of the past, then you're never going to make a prediction that's above the highest data point. And just looking at the data, we would expect that the future values would be above the observed data points. Like I said, I think that green dot's going to probably be a good prediction. But if I'm just doing averages of the past, I'm probably going to get an estimate that's somewhere like where the red dot is, kind of in the middle of the vertical middle of those different dots that I have. And so if there's a noticeable upward trend, and if I take averages as my prediction, then I'm always going to be under predicting. I'm never going to be making a prediction that is as high as it should be. Or if the data that you're looking at has this noticeable downward trend, then again you would think that the estimate should be somewhere where the green dot is. But if you're using an average of the past data, then you're going to get some value that's somewhere near the red. So the averaging technique is useful if there's no noticeable upward or downward trend in your data. There are different ways you can average, I guess. You might think of just saying, well, let's just start with the very first observation, the very first piece of data that I have, the farthest back that I can go. And I'll just see, just add up every single month of sales data that I have. And so I'm starting from the very beginning that I have, and I just average it all up, and I say that's going to be my prediction for the future. You can do that, and there are other ways, though. You might think that, well, if the first piece of data that I have is, January of 2000, and here I'm sitting in 2013, whatever, knowing what the sales were in January 2000 might not be all that helpful. So you might say, well, I really only want to maybe go back 6 months, and let's look at the past monthly sales for the past 6 months. And I'll make a future estimate based on the past 6 months of sales. And so what you're doing is you're taking a moving average, because if you said, well, here January, February, March, April, May, June has happened. January through June has happened, and I want to make a prediction for July. So what you would do is you would take the average of the January, February, March, April, May, June sales, take that average, and again you can kind of see that I'm doing XT, and then would be maybe the June, XT minus 1 would be the May, all the way back to January. You just take the average of those, and that would be your guess for July. Well, once July arrives and you want to make a prediction for what August is going to be, then you wouldn't include the January variable anymore, because that would be 7 months back. You would basically be doing February through the observed value of June, what actually happened in June. So February, March, April, May, June, July. Sorry, that's right. We said July. We wanted to predict for August. So you would take February through July as your 6 months that you are averaging. And so you can kind of see what's happening is that you're taking an average, but the months that you are averaging is moving as the months go by. So again, when you're trying to make a prediction for October, then you would say, well, let me, the most recent data that I have is September, and let me go back 6 months from September. So your average is moving. Of course, they call it a moving average. That's nice, and what it does is, again, it allows you to not have to worry about all of the past data that you have. One sort of, I guess you can think of it as a drawback, is that it gives equal weight to all of the months of data that you have. And again, that might be somewhat helpful in some situations, maybe not so much in others. You might think that, well, I do think that the past 6 months is helpful, but obviously the most recent month might be, I should give more weight to that, and maybe not so much weight, still some, but not so much weight on what happened 6 months ago. So there's some ways you can get around that too. One of which is this exponential smoothing technique. And this kind of allows you to make future predictions based on basically how successful you were at making predictions in the past. So I can say, well, I had this guess of what I had this prediction of what I thought was going to happen in time period t prime, the t with the little apostrophe over it. And then, so that was my prediction that I had last month. So when it was in June, I made a prediction of what I thought would happen in July. So that was that guess was that xt prime. But then I can actually see what happened in July. I can see what actually happened. That would be my xt by itself. And so you can kind of, again, make a prediction for the future based on what you thought was going to happen and what really did happen in the previous month. And you can assign different weights to those things. There may be situations where what actually happened was kind of a weird thing. Maybe there's a bad storm or something, and so what actually happened was kind of out of the ordinary. Or you might have thought that maybe your prediction was just unusually bad, and so your prediction was kind of out of the ordinary. And you might want to give your prediction less weight, and what actually happened, you might want to give that more weight. And so this exponential smoothing technique, which Excel can do also, Excel does moving averages also, you can do this exponential smoothing technique. You can see it in the data analysis tab. And of course they changed around a little bit. They, instead of having this W variable, they call it a damping factor. I don't know if it has anything to do with rain, but it's 1 minus this damping factor would be what we would consider here to be this value of W. A few little tidbits to be concerned with as we're coming up with these data estimation techniques and these forecasting techniques. Obviously, if you have monthly data that go through March 2008, making a prediction for April 2008 is pretty straightforward, probably not that dangerous, I guess. Making a prediction for April or May, June, a couple of months in advance wouldn't be all that scandalous. But obviously, if all you have is data through March 2008 and you're trying to make a prediction of what's going to happen in March of 2045, then you probably shouldn't have a whole lot of confidence in that. So the further out you go, the further away you are getting from the data that you actually used to come up with this estimation. And, of course, you put more asterisks by that thing and say, don't really believe this. Or don't have as much confidence in this because it's so far out from the data that I've actually used. Of course, we always want to try to have the best theory driving our model. We want to have the appropriate variables included in our model. And so if there's something that you didn't use, something that you didn't include, something that you threw out when you shouldn't have, then of course that's going to make your forecast not as reliable. So this just goes back to having a good step one, thinking about the theory, thinking about the variables that you think are important. And there's always things that are going to happen that you're not going to be able to predict. There are always going to be things that happen that you aren't going to be able to get data on either. And so, forecasts are never perfect. They are always subject to some degree of error. And of course, a good forecaster admits that and still makes predictions, but says, obviously, again, past performance isn't predictive of future results. So, but again, don't let that hamper you from using the tools of forecasting and using some of the regression analysis that we've talked about. Again, it's fairly simple to run these regressions, and they can provide a lot of good insight. Again, you just might want to always sort of temper past predictions that you've done with what actually happened to give you a sense of how accurate your predictive models are.